Hello and welcome to section 3.4, concavity and the second derivative test. In this section we're first going to define concavity, and basically we have to have a differentiable function and the graph is concave upward if the slope function is increasing, and concave downward if f prime is decreasing. We also have the graphical interpretation of this, and basically when we have a graph that is concave upward, the slopes of the tangent lines will always be below the graph, and when the concavity is down, then you'll have all the tangent lines below, the graph will be below all the tangent lines. And so that's kind of what we're talking about, and this is just kind of something that we need to kind of pay attention to, so please make sure you get this down. So then, how does the concavity affect the original graph? Well, we have these open intervals here, and we have this graph. The original function is 1/3 x cubed minus x. Is concave downward on the open interval from negative infinity to 0, and you can see that right here. Well, f prime of that function is x squared minus 1, and is also decreasing there. So you could see that if you look at the graph in that interval from from negative infinity to 0, you could see down in this graph down here that all the slopes down here are negative. They're all a negative slope. They're going downhill. And so then if the graph then turns concave upward, which it does after 0, from 0 to positive infinity, then you can see that all the slopes of this graph are up. So then basically, when the slope is positive down here, we're concave up on the original graph, and when the slope is negative on the derivative graph, then we're concave downward. So we're going to have to use a second derivative to find the slope on the derivative graph. Now here's the other thing. You'll notice that when we have a maximum on our original graph, you'll notice that on the derivative graph, it's down here, it's crossing the x-axis. So things to notice is when we have a max or a min, we're crossing the x-axis on the derivative graph, and when we are changing concavity, you'll notice that, hey look, we have a horizontal tangent down here on the graph when we have a change in concavity. So that's how we're going to actually use this. We're going to use our test of concavity. So we're going to look at the second derivative, and if the second derivative, the slope of the derivative graph, which is the second derivative, is positive, then the graph will be concave upward. If the second derivative is negative, then it's going to be concave downward. But there is a third case that happens, and it's when the second derivative is equal to 0, then f of x was linear to begin with, and there's no concavity to define. It was a straight line to begin with. So straight line is neither concave up or concave down. So things to think about when you're doing this. So please make sure you copy this stuff down. And then the next thing that we're going to talk about here, well, we'll do an example. We're going to go through and determine the concavity of the graph. So since we're trying to find where this graph is concave down, we're going to use, without graphing it, we're going to go ahead and use the second derivative use the second derivative here and go ahead and find out what's going on. And so if we were to take the first thing I probably would do is rewrite the function as 6 times x squared plus 3 to the negative 1. It's not a product rule because 6 is not, doesn't have an x, it's not a function. It's not a quotient rule because 6 is not a function. You could use both of those, but it would end up coming out in the wash that you didn't need to. So if I take the derivative of this function, I leave the 6 alone, multiply by negative 1, that's my power rule, x squared plus 3. And reduce the power by 1, and then I got to take the derivative. This is my chain rule though, and I get 2x. So my first derivative function will look like this. It looks like I get negative 12x over x squared plus 3 squared, or negative 12x times x squared plus 3 to the negative 2. Well, in either case, if we were to go ahead and set this equal to 0, you would see that 0 is the only place where only place where I can actually get a value, because when I set this guy equal to 0, so my critical number in this case is that x equals 0. This bottom one, I'd get an imaginary number, and I don't want to do that. Now, unfortunately, I've got to do a product rule and a chain rule in order to take the second derivative, so that's where I'm headed. And so derivative of the first will give me negative 12. Leave the second alone. Then add on, leaving the first alone, and taking the derivative of the second. So here's my chain rule. Negative 2 x squared plus 3 to the negative 3, and then the derivative of the inside, which was 2x. All right, so this becomes quite a jumbled mess here. Let's see, I get negative 12 over x squared plus 3 squared, and on this side it looks like I get 24 positive 48 x squared over x squared plus 3 cubed, I think is what I end up with. And unfortunately at this point it's hard to set equal to 0 because there really isn't anything in common, and it's just too big of a jumbled mess. So I'm going to have to do a little simplification, and so this guy over here is going to get multiplied by x squared plus 3 top and bottom, which is my convenient form of 1. So the top of this thing will change into negative 12x squared minus 36, and then I have my plus 48x squared, and then on the bottom down here it now becomes all of x squared plus 3 cubed because I multiplied and got the extra one. So f double prime of x will turn into 36x squared minus 36 all over x squared plus 3 cubed. All right, and I could maybe make my life a little bit easier and factor out a 36. So f double prime of x, all neatened up, would be 36 times x squared minus 1 all over x squared plus 3 cubed. All right, so now if I set the second derivative equal to 0, I have to check the bottom is still going to be an imaginary number, so we don't want that. So we really worry about the top, and you can see that my what we're going to call points of inflection happen at x equals plus or minus 1. And I get that by setting 36 times x squared minus 1 equal to 0, which gets me x squared minus 1 equals 0, which means x squared is equal to 1, and then when I take the square root, I get plus or minus 1. Okay, so now I have these points that I am dealing with, positive 1 and negative 1, and so I have to set up some intervals to figure out what's going on. So I'm going to go from negative infinity up to negative 1, and I'm going to go from negative 1, and I guess I should probably do this, to positive 1, and then from positive 1 to positive infinity, and I should probably, well, anyway, so I get this. And so then at this point, I just have to pick a value and plug it into f double prime. So this is my f double prime row, and if I plug in, well, a good number less than then negative 1 to negative infinity would be something like negative 2. So f double prime of negative 2, the value I'm plugging in, well, plugging that into this function, I'm going to get 36 times negative 2 squared minus 1 all over negative 2 squared plus 3 cubed. Now, you could probably in your head figure out whether, we don't care what the actual number is, we just care whether it's positive or negative. And you could see that on top here, this is going to turn into positive 4 minus 1, which is 3, so the top is positive. And on the bottom, that's a fraction bar there, on the bottom, negative 2 squared is positive, so I get positive, positive. So this graph is positive. So from negative infinity to negative 1, this is increasing, so this means the slope of the derivative function is increasing, so that means we are concave up. Well, between negative 1 and 1, a good value to pick for f double prime would be 0, and so it's really going to be 36 times 0 squared minus 1 all over 0 squared plus 3 cubed. Well, on top up here, you can see I'm going to get negative 36, so I'm going to have a negative on top, and then on the bottom of my fraction, it's going to be 3 cubed, which will be positive, so I get a negative and a positive, which means I'm negative. So between negative 1 and positive 1, I am concave down. And then finally, between f double prime of something greater than 1 to infinity would be something like 2, and again, it's going to be 36 times 2 squared minus 1 all over 2 squared plus 3 cubed. Again, I don't care about sign, I just care about signs. This is 4 minus 1, which is going to be positive, so the top will be positive. And on the bottom, you can see that's going to be positive. So here we are concave up again. So that's really what we're looking for, are intervals of where we are concave up and concave down. And so what we have done there is I gave you guys a hint that if we set f double prime equal to 0, we're looking for points of inflection. Those are the places where the graph changes concavity. And so, and it doesn't have to change concavity there, but it's a place where it could change concavity. And so it's f prime is 0, f double prime is 0, or not differentiable. So we got to check like the bottom of the fractions also. That's like in this previous example, I had to check and make sure that this guy right here, or actually this guy on the bottom, the x cubed, was not equal to 0, or I was not a number, because I would test around that point also, like I did in the next example. So make sure you guys get these down. Make sure you understand. Come in questions if you have any questions about points of inflection. And then finally, what we basically did there was the second derivative test. So if a function has f prime of c equals 0 and the second derivative exists on an open interval, so basically we're saying we have a maximum or a minimum exists and we have an open interval, then f double prime is greater than 0, we have a relative maximum. If f double prime is less than 0, we have a min. I've switched those, sorry. If f double prime is greater than 0, then we should have f of c should be will be a minimum, yes. And so that's what it's telling me, that if I have, if I'm concave up, if my second derivative, the slope of my derivative function is all concave up around this c value, then you're at a minimum. And then f double prime is, if you get if it's less than 0, then you're at a maximum. So that means that all the slopes around it are going to be negative and would mean you're at a maximum. And of course, if f double prime equals 0, then the test will fail. You won't be able to tell whether you have a maximum or minimum. You'll have to go back to the first derivative test, and the first derivative test will tell you what's happening with the slopes, and most likely you'll be increasing around the point, or decreasing around the point. So please make sure you get all of this stuff down. Make sure you come to class if you come to class with your questions, and we will talk more about this and have plenty of time to practice it.